Hello everyone, I'm Norman Wahlberger, and I'd like to welcome you to this new series called Famous Mathematical Problems. So what I intend to do is to treat with each video a different famous mathematical problem. The intended audience is, well, first of all, undergrad math majors or college students who are taking some mathematics, and the general public with an interest in mathematics and in particular in problem solving. So the range of mathematics can very roughly be divided into two kinds of things, into theory and problem solving. So I have lots of other YouTube video series which are more or less concentrated on theoretical developments in making a sequence or continuous study of some particular topic. So in particular, I have a series on linear algebra, one on math foundations, one on rational trigonometry, one on hyperbolic geometry, a series on history of mathematics, and a series in the elementary mathematics from K to 6. So you might be interested in some of those series as well. So those series are more or less continuous, that each video builds on the previous. This one here is going to be more freeform and more relaxed in the sense that all of the videos are going to be more or less independent from each other. So if you haven't managed to really understand one of the videos, it might be that the next one will be much easier for you to understand. They're each going to be more or less separate, independent videos where I concentrate on one particular problem. We look at that problem from different points of view. Maybe we give some hints, maybe we give some secondary, simpler problems for you to work on. Alright, so we're going to concentrate on the problem-solving side of mathematics in this series. And I'd like to make a special thanks to Professor Saad El-Zanaati, who I had breakfast with one day at a conference in Bangkok, and I was telling him about my YouTube series, and he said, why don't you make a series on famous math problems? And I thought that's an excellent idea. So I'm taking up his suggestion. Thank you, Saad. So we're going to treat a wide range of problems, some of them going back a long time to the ancient Greeks, and some of them are relatively modern. And I want to be able to assess very roughly the difficulty level of the problems. So we're going to introduce a scale, a difficulty scale, which is very, very rough. It's no doubt quite inaccurate. It's just my own guesses to various things. So when we're talking about solved problems, problems that are either well known, they have solutions, or it's not too hard to see that someone could come up with a solution, then we'll assign generally the difficulty level 1 to 5. And roughly what we'll think is that difficulty level 1, which is the easiest, will correspond to roughly an hour's thinking on the part of, say, a bright but not genius undergrad math major. Difficulty level 2 maybe requires a day of thinking. You have to get up in the morning, you have to think about the problem all day, and then maybe you can get a solution. D equals 3, these are problems that require maybe several days of thinking, maybe around a week. D equals 4, a month of thinking. And D equals 5, very serious problems that probably require a year or perhaps more to crack these problems. Now obviously these are very inaccurate, and they depend very much on the individual. What one person might take an hour to do, somebody else might take 3 days to do, someone else might take 5 minutes to do. But I'm just using sort of averages and ballpark estimates here to roughly allow us to position a problem in terms of its difficulty. And these are just my guesses. For our unsolved problems, well, things are a little bit more difficult to assess because these are, after all, unsolved problems. And an unsolved problem, you don't really know how hard it is going to be until you actually solve it. So we're going to generally use the scale 6 to 10 for the unsolved problems. And let's say that D equals 6 requires roughly a year of work. So it may be an unsolved problem, but I'm pretty confident that if someone spends a year thinking about it, they have a pretty good chance of getting it. And when I say a year, well, it might be 6 months or it might be 2 years, something in that area. A D equals 7 level problem maybe requires 10 years of effort. It's a serious problem. You need to dedicate a good chunk of your life to tackling this problem. D equals 8. Well, at that level, probably you're not going to be able to do it. The average person is not going to be able to solve this even with a lifetime of work. It's maybe going to require a century of effort, so combined effort, maybe 5 people, group of 5 people working their entire career, something like that. And D equals 9. Well, these are very serious problems. These are things like Fermat's last theorem and the 4-color problem and so on. So these are problems that a single individual cannot really expect to crack in less than a millennium. Okay? So you need teams of people working for a long, long time to ultimately crack these things in general. And then the top level, D equals 10, these are problems which are essentially impossible in my opinion. So we're going to use this as a rough guide. I'm going to assign to all of the problems some estimated difficulty level, a number from 1 to 10, and that will alert you to roughly how difficult I think the problem is likely to be for your average undergraduate. So here's a few words about my aims with this series. I hope, first of all, to bring interesting mathematics to a wide audience. Secondly, I want to channel amateurs' interest and effort in rewarding directions. I know that there are a lot of people out there who would like to do some mathematical work. Not just a question of learning some particular subject, but actually getting their hands dirty and doing some mathematics, some research-type mathematics. And it's not so easy for amateurs to do that. And it's I know from the correspondence that I've had with people that sometimes there's a danger that amateurs drift off in philosophical directions and spend a lot of time and energy doing something which maybe is really not that valuable. So I'm trying to lay out some paths here that amateurs, retired people, or not very young people who are interested in mathematics can go down to get themselves working in a research kind of situation. So there's going to be problems to do, things to think about, things to work on. Some of them rather open-ended, of course. So I want to give people worthwhile challenges of the mathematical kind. I also would like to impress on educators the importance of good exercises. So if you're writing a book, a mathematics book, of course the theoretical side is very important, but there's this other side, the flip side, which is the side of exercises and problems. The things that are at the back of the chapters, for example. And that side of things is almost as important as the theoretical side, in my opinion. And it often gets shortchanged in many traditional textbooks and courses. We've lost sight of the idea of providing interesting and stimulating problems for people to work on. It's too tempting to give people rote, sort of boring, do the same thing that I did kind of problems. So I want to get educators thinking about the nature of the problems that they're assigning students and the interest of those problems. It's an important aspect of mathematics education. I want to encourage young people to study mathematics. The greatest human intellectual endeavor, mathematics, and it's so interesting and it's so rich and full, and it's just a much better way of spending your time than doing a lot of other things that I think young people can get steered into. All right? So I'd like to present the idea that mathematics is cool and it's fascinating and it's interesting and it's something that you as a young person or not so young person can dedicate yourself to. And then I have a rather selfish motive. I'm just interested in learning about some new topics. So having to present problems that I don't know that much about forces me to learn some mathematics, and that's a good thing that I value. So that's enough of introduction. Now let's roll up our sleeves and get into it. So our first problem is one of factoring large numbers. And specifically, I have a very specific problem. This is famous math problem number 1. So this is the first of our problems. It is find the prime factorization of this number z. And z is 10 to the 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 10 plus 23. It's a pretty big number, and the problem is to find its prime factorization, to write it as a product of prime numbers. And I've started with a problem which is not very easy. In fact, the difficulty level of this problem is 10. This is, in my opinion, an impossible problem. This is too difficult to solve. It's an unsolved problem that will forever remain unsolved. No matter how sophisticated our computers get, no matter how widespread across the universe we might become, and how intelligent we are, or maybe some other races, no one in the universe is ever going to be able to factor this number, in my opinion. Okay, so why am I starting with this problem? Well, first of all, it's intrinsically interesting. The question of factoring numbers, especially large numbers, is an important one. And it connects naturally with the prime numbers, which are a fundamental and interesting object in mathematics. They're very fascinating. So let me remind you, the prime numbers are those numbers that don't have any factors other than 1 and themselves. So 6 is not a prime number because it can be written as 2 times 3. So 6 is a composite number. But 7 is not expressible as A times B unless you use 1 times 7. And so that makes 7 a prime. And here are the list of prime numbers up to about 73. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 60, 71, 73. So I hope I haven't left out any or made any mistakes. And we know from the ancient Greeks that the prime numbers keep going, in the sense that, as Euclid pointed out, that if anybody has what they claim to be a list, a finite list of all the prime numbers, then they're wrong. There's some way of concocting a bigger prime number which is not on their list. Something else very important that the ancient Greeks understood is the fundamental theorem of arithmetic, which is behind this problem. And the fundamental theorem says that every natural number can be written uniquely, well, uniquely up to order, as a product of primes. So you take some number like 24. Well, 24 can be factored in a number of ways. It can be factored as 4 times 6, or as 3 times 8, or as 2 times 12. So if we take one of those factorings, say 2 times 12, then 2 is a prime, but 12 can itself be factored as 3 times 4. And 4 can itself be factored as 2 times 2. So altogether, 24 can be factored as 2 times 2 times 2 times 3. And each of those are primes. 2 times 2 times 2 times 3, that makes 24. So we've factored it into primes, and those primes are unique. There's no other way of factoring 24 into primes except to use 3 2's and 1 3. And that works not just for 24. The theorem is telling us that works for any number, even very big numbers. So this is a very big number, and the theorem says that it can be factored as a product of primes. And the problem is to actually find that factorization, and I'm saying that that's too hard. That's an impossible problem. But nevertheless, it's quite interesting because it introduces us to this idea of factoring. And that's very interesting. So when faced with a problem that's difficult, maybe difficult because it's a big problem, it's sensible to look at simpler versions of that problem, to be more modest and say, well, let's start with something easier and see if we can understand that. So let's look at some much simpler variants to our famous problem number 1. Okay, let's have a look at 10 plus 23. Well, 10 plus 23 is 33, and that factors as 3 times 11. How about 10 squared plus 23? 10 squared is 100, so that's 123, and that factors as 3 times 41. 10 cubed plus 23 is 1,023. That factors as 3 times 11 times 31. 10 to the 4th plus 23 is 10,023, which factors as 3 times 13 times 257. 10 to the 5th plus 23 factors as 3 times 7 times 11 times 433. 10 to the 6th plus 23 factors as 3 times 333,341. 10 to the 7th plus 23, 3 times 11 times 19 times 41 times 389. 10 to the 8th plus 23, 3 times 2,293 times 14,537. 10 to the 9th plus 23, 3 times 11 squared, so there's 2 factors of 11, times 61 times 45,161. And 10 to the 10 plus 23 is 3 times 13 times 29 times 8,841,733. But instead of saying that, I'll just say 8,841,733. All right, so that's some kind of initial list, sort of slowly approaching the form of RZ. Various powers of 10 plus 23. What's so special about 23? Well, actually nothing particularly. It's just something I've more or less chosen at random. What we're just looking here is looking for some kind of pattern in some reasonably well-defined sequence of numbers. Now, it should be kind of reasonably obvious that there's some pattern in these things, but more or less it's a little bit random. 3 happens to be a factor of all of them, and that's obvious because a number like this is divisible by 3 precisely when the sum of the digits is divisible by 3. And the sum of the digits for all of these numbers is always 6, because there's a 3, there's a 2, there's lots of zeros, and there's a 1. So all of these numbers have to be divisible by 3. There's a factor of 3 everywhere. In particular, the number z is certainly divisible by 3. We also notice that every second one is divisible by 11. And that's not too hard to see. So something like this here, for example, is divisible by 11 because if you take every second digit and add them up, you get 3. And then you take every other second digit, 2, 0, and 1, you also get 3. The difference is 0. That means it's divisible by 11. So that's pretty easy to see. Everything else is a little bit more mysterious. It seems as if the other prime factors, especially these bigger ones, are pretty well popping up at random. There's no conceivable pattern. But we haven't gone very far, so let's go a little bit further. So here are a few more factorizations of numbers that are a little bit like our number z. And in fact, I've obtained these using my computer. I have a nice program there called Scientific Workplace that I use to write my mathematical papers. And that has a mathematical engine inside which allows me very quickly to factorize some number. So I just write this number here and I press factor and boom, it tells me that the factors are like this. And for a number of this size, it's almost instantaneous. It takes no time at all for my computer to calculate that. Now, if you don't have a program like that, and there are many mathematical programs that will do that, you can go online these days. And you can do it over the internet using Wolfram Alpha. This is a very interesting program, the brainchild, or one of many brainchilds of Stephen Wolfram. And it's a lovely program, and one of the things that it will do, amongst many other things, is make calculations for you. And so, for example, it will factor pretty big numbers. It'll factor all of these numbers for you, and you can do that in your browser. So let's have a look. 10 to the 11th plus 23. All right, we have 3 times 7 squared times 11 times this number here. 10 to the 12th plus 23. There's a 3. There's a 41, which has appeared a couple times before, and then some other numbers. 10 to the 13th plus 23. Those are the prime factors. 10 to the 14th plus 23. There's 3 times 1289, then this rather big one. And then my favorite, 10 to the 15th plus 23, is 3 times 11 times, and this wonderful prime. Okay, this is a prime that's read 30, 30, 30, 30, 30, 30, so 6 30s, and then the next one is 31. So if someone asks you for a big prime, maybe you can remember that one. 6 30s followed by a 31, that's a prime number. Okay, then one can keep going, and here is, after a little jump, 10 to the 20 plus 23. 3 times 71 squared times 151 times 223 times this. 10 to the 50 plus 23, which is getting to the limits of the computational ability of my computer. This is the biggest one that I calculated. So it's 3 times 5003 times this number. This is all one big number. That's a prime number. So it takes my computer a minute or two to calculate that. It's not that long, but it's really remarkable that it can figure out that that's a prime number. I hope it does that right. Okay, I tried to find the factorization of 10 to the 100 plus 23, which is certainly doable, but my computer was taking too long to do that, so I can't do that. So here's a challenge. First of all, can you find any patterns here? And can you prove them? And secondly, can anyone find factorizations of bigger numbers of the same form? So we're talking about 10 to some power plus 23. So maybe we'll see what the record is. Can anybody get 10 to the 100 plus 23, for example? All right, so it's quite remarkable that we can do this so easily with our computers. Euler or Gauss would have been enormously jealous of us being able to do this. And I think if they came to the modern world, of course they'd be very impressed with our cars and our trains and our planes and so on. But they would probably be most impressed by our computers and the ability of our computers to make these incredible calculations so quickly. Euler and Gauss, perhaps they would have had thoughts like, why are not young people spending all their time on their computer factoring numbers and trying to find interesting patterns? This is such a powerful tool, and we're somehow investigating this primordial beauty, the factorization of numbers. It's some kind of fundamental, interesting, God-given loveliness. So how do we go about actually factoring big numbers? Well, that's an important mathematical problem on its own. And there are very sophisticated advanced techniques these days for doing that. But initially, at least, the idea is relatively simple. If you have a big number, like 10 to the 100 plus 23, and you want to factor it, what you do is you test it for divisibility one prime at a time. So you divide it by 3. And then the quotient, you see if it's divisible by 5. It's obviously not divisible by 5. So then you check divisibility by 7, and then by 11, and then by 13. And if it's not divisible by 13, whatever, then you say, okay, we'll just go to the next prime. And if you find a prime that is divisible by, well, then you divide it by that prime. You get a slightly smaller number, and you keep going in your list of primes. This sounds very simplistic, and it is, but there's not much better ways of doing things at the elementary level, at least. So all of these considerations with factoring and divisibility are made much simpler by learning a little bit about modular arithmetic introduced by Gauss. So this is not a proper introduction. I just want to state the main definition and two important results. And if you are interested in the factorization problem, please learn about modular arithmetic. It's a key technology for talking about this kind of problem. So Gauss said that if you have two numbers, a and b, then we'll say that they're congruent with this triple equality sign. They're congruent mod m, or modulo m, precisely when a and b have the same remainder when divided by m. So for example, if m happens to be 5, then 3 and 8 are congruent mod 5, because 3 and 8 both have the same remainder when you divide them by 5, namely 3. And other numbers that are congruent to 3 mod 5 would be 13, 18, 23, 28, 33, 38. Whenever you add 5, you're basically getting another number which is congruent to the one that you started with, mod 5. Another way of saying that is that m divides the difference between a and b. And we sometimes write that this way. It means m divides a minus b. Okay, there's two important basic results in this theory, both of them somewhat non-trivial. Fermat's little theorem that if p is a prime number and a is a number that's relatively prime to p, that means it doesn't share any factors with p, and if p is a prime, it means, well, that it's not a multiple of p. Then, if you take a and you raise it to the p minus first power, you're going to get something that's congruent to 1 mod p. So for example, if p happened to be 7, and let's say a was 2, then 7 minus 1 is 6. So this theorem would say that if we take the number 2 and we raise it to the 6th power, we should get something that's congruent to 1 mod 7. So is that true? Well, 2 to the 6th is 64. Is 64 congruent to 1? What's the remainder when you divide 64 by 7? Well, 64 is equal to 63, which is a multiple of 7, plus 1. So yes, the remainder is 1. So that's a true statement in the case when p is 7 and a is 2. And the theorem says that that holds more generally. And then Euler came up with a generalization of that where the modulus p did not necessarily have to be a prime number. If m is just some general number, like a composite number, then if a is still relatively prime to m, then the formula is this, that a to the phi of m is congruent to 1 mod m. So that generalizes this. But I have to tell you what is phi of m. This is the Euler-Toschen function. So phi of m is, it's the number of numbers in the range 1 through m minus 1, which are relatively prime to m. So for example, if m happens to be 8, let us say, then what is phi of m? Well, we have to count the numbers in the range 1 through 7, which are relatively prime to 8. And those numbers are 1, 3, 5, and 7. And so phi of 8 is 4. So the theorem says that if m is 8, then a to the 4th is congruent to 1. So for example, so we have to choose if a is relatively prime to m, say a is equal to 3. Then if we take 3 to the 4th, it should be congruent to 1 mod 8. What is 3 to the 4th? It's the same as 9 times 9, it's 81, and that is congruent to 1 mod 8. All right, so these two results allow us to more efficiently check whether big numbers are divisible by something or another, by checking what they're equal to mod that number that we're wanting to divide by. Okay, that's a very lightning fast introduction to modular arithmetic. So we're not doing things very systematically in this series of lectures. We're just presenting highlights, so I'm often going to ask you to maybe go off and investigate something further if you want to learn more about things in this direction. So modular arithmetic, which you can learn from many places, is a key tool for talking about these kind of divisibility and factorizing problems. So let's go back to our famous problem number 1. This number z and its prime factorization. So we've established that 3 divides z because the sum of the digits is divisible by 3. Does 5 divide z? No, because the final digit is a 3. And if it's divisible by 5, it's got to end in either a 0 or a 5. So it's not divisible by 5. The next prime is 7. So we can ask, is z divisible by 7? So how do we figure that out? Well, we use the Fermat theorem. 7 is a prime, so we're asking, does 7 divide z? So let's work mod 7. Okay, so we're interested in 10 to some big power. And when we work mod 7, 10 to whatever power, say m, is really the same or congruent to 3 mod m, because 10 and 3 are congruent mod 7. So we can replace the 10 at the bottom of this chain with a 3. when we're working mod 7. And then the exponent is, well, 10 to the 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 10, 9 times. 3, 6, 9. Okay, so what we're going to now ask is, let's change to mod 6 for a second. So that's prime p, then p minus 1 is 6. Remember, Fermat's theorem tells us that a to the p minus 1 is congruent to 1 mod p. So if we look at the exponent from the point of view of what is this number when we express as a multiple of 6? What is its remainder if we divide it by 6? So let's have a look at this following thing. So this exponent, looking at it, the base is 10, and mod 6, that's congruent to 4. They have the same remainder. When we square 4, we get 4 squared, which is 16, which is also congruent to 4, because the difference is 12. So 4 squared is congruent to 4. If we multiply by 4 again, we'll still get 4. So any power of 4 is congruent to 4 mod 6. In particular, this whole expression, which is 4 to some power, we don't care what power it is, 4 to some power, it's got to be congruent to 4 mod 6. Meaning that this exponent m is 6 times some number plus 4. That's what it means to be congruent to 4 mod 6. It means that it's a multiple of 6 plus 4. So we've established that by looking at m mod 6. Alright, now let's go back to mod 7. We're actually interested in this number z here, which is 10 to the m plus 23. 10 to the m is the same as 3 to the m when we're working mod 7. Alright, 3 to the m plus 2. Why is 23 the same as 2? Well, because the difference is 21, which is a multiple of 7. So we can replace the 23 with just 2. Now this 3 to the m, we've just seen that m is 6k plus 4 for some number k. And that's good because we can write that now, we can write this part as 3 to the 6th to the k times 3 to the k. We're using the law of exponents there. And 3 to the 6th, we know that's congruent to 1 mod 7. That's the Fermat theorem. It's something 3, which is relatively prime to 7, raised to 7 minus 1. So that's congruent to 1, and so any power of it will also be congruent to 1. That's the way modular arithmetic works. Now that's why we did this business with the 6, to get that 6 there, so that this would simplify to a 1, and that whole thing simplifies. 3 to the 4th is 81. So we're getting 81 plus 2, and 81, if you divide that by 7, take out 77, it leaves 4, so we get 4 plus 2. So my calculation is that the remainder when you divide z, which is what we started with, by 7, is 6. In other words, z is not divisible by 7. It's divisible by 3, it's not divisible by 5, it's not divisible by 7. 7 does not divide z. Oh, that was a fair amount of work. It was a fair amount of work because our number z is ridiculously big. Okay, that's the way mathematics is. When the numbers get big, the calculations get harder. So although our primary problem may be intractable, nevertheless there are simpler versions or related problems that emerge from looking at this that are perhaps quite doable, challenging. So, first one, other than 3, which primes p less than 100 divide z? So we've ruled out 5, and we've just ruled out 7. What about the other primes less than 100? Do any one of them divide z? Okay, so that's a fair amount of work. So I suspect that might be, a week or a month's work for someone interested. It's something you can think about if you have some number theoretical interest. If you pick a prime, say p equals 17, and then you choose some random big number, then roughly you expect that there's a 1 over 17 chance that that big number is divisible by 17. Because every 17th number is divisible by 17. So we would probabilistically expect that some of the primes less than 100 divide z. There's at least a reasonably good chance of that happening, although it doesn't guarantee that it will. And then, the second exercise, what is the quotient after we divide z by the product of its prime factors? Suppose that you find out that the prime factors are 3, 31, and 37. Okay. So that means that you can then divide z by the product 3 times 31 times 37. And you're going to get a quotient. The problem is, how do you write down what that quotient is? So it requires that you first done this exercise. So maybe if we can figure out what that is, then we can ask, well, how do we actually write down the quotient? So although z itself is reasonably easy to write down with all these 10 to the 10 to the 10 powers and so on, dividing it by something like 3 times 31 times 37, that's going to be much more problematic to write down in some kind of sensible way. So even thinking about how to orient yourself to that problem, I think, is interesting. Okay, and another exercise. What is the largest n for which we can write down a prime factorization of 10 to the n plus 23? I've mentioned this already. We've written down some factorizations for small n. I wrote down one for 50. What's the record? What's the biggest n that we can stick in here so that we can actually write down a prime factorization of this? So I started by making this claim that this famous math problem number 1 is actually unsolvable. It has difficulty 10. So why is that? Well, so I claim that it's almost surely impossible. The number z that we've chosen is actually very special. Why is it special? It's because it's very big, but it can be written down very simply. It's a huge number, but we actually wrote it down on just essentially half a sheet of paper like this. Most numbers less than z are very different from this. Most numbers less than z require vast amount of space to write down. In fact, it's worse than that. Most numbers less than z cannot even be written down in our universe because our universe itself is too small. There's not enough room in our universe to write those numbers down in any fashion whatsoever. And that's true of most of the numbers less than z. Now, in particular, most of the prime factors of z probably don't exist. That sounds like a strange statement. Okay? The things that we think about when we're thinking about prime factors, it breaks down when we're starting to talk about numbers of the size of z. Because these prime factors, if you actually wrote them down, you would require more room than we have in our universe. So it starts being a philosophical question. What does it mean if there's no way of writing or accessing this prime? And when I say, write down in the universe, I mean by any means whatsoever. I don't mean just as a decimal expansion. You can write down any system you like using exponents and factorials and who knows what. The point is, no matter what system you write down, you are not going to be able to write down most of the numbers less than z. So this whole discussion, I'm going to talk about this in the Math Foundation series at some point, because it's an important part of my philosophy and way of thinking that we must respect the size of big numbers. The current idea that the number system is pretty well uniform and just things get a little bit bigger and bigger, but more or less everything still is true as we get bigger. This is very, very far from the reality of things. Okay? What happens is that almost everything that we know starts breaking down when the numbers get big. That is why this exercise, this problem, is so important, because it starts to teach us that. It starts to teach us that big numbers are different. The size of the universe has something to do with mathematics. Now, what happens if the physicists are wildly wrong and the universe is much, much, much bigger than they currently think it is? Which, of course, could very well be. Well, in that case, my claim has to be weakened a little bit. If the universe is vastly bigger than we think it is, then I might be wrong about this. That it might be, in fact, that the difficulty is only 9 plus plus. There might actually be enough room in the universe to write down the primes. But if the universe is anywhere near as big as physicists currently think it is, then there's not enough room, and that prime factorization just doesn't exist. Whether we like it or not, whether it fits with our ideology or not. Okay? So the painful fact is that the fundamental theorem of arithmetic is not really true. It's only true up to a point. All right, so if you're interested in that kind of thing, and many other things besides, have a look at the Math Foundation series. So we learn something by studying these famous big problems, and so this problem of factoring big numbers is a very interesting and important problem. Even though the particular one that I've given you here is admittedly rather ad hoc, but it illustrates many of the important points. All right, in our next video, we're going to look at a famous unsolved problem that's very well known and that a lot of people are working on. It's called the Collatz conjecture, or the 3n plus 1 problem. It's very interesting, it's very accessible, it's in fact in some ways much simpler than this one, and you yourself can try to have a go at solving this problem. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.